Hello, it is Monday, April 18th, and today we're going to be doing part 1 of homework 6. So, first things first, Raoult's law states that the mole fraction of the liquid phase multiplied by the vapor pressure is equal to the mole fraction of the vapor phase times the pressure, or the partial pressure. So basically, the partial pressure is equal to the mole fraction times the vapor pressure. So the first thing we need to talk about is the bubble point. The bubble point is when the first bubble is created. It is not the boiling point, it is not the evaporating point, it is the point when the first bubble is created in a system. So in this system here that I've created, we have benzene and toluene in a mixture under 1 bar of pressure. So, let's look at Raoult's law. So, in order for us to be at the bubble point, a couple things need to happen. We need to be at the specific bubble pressure and the specific bubble temperature. Now, the specific bubble pressure occurs when the partial pressures of both benzene and toluene added together equal the pressure forced against the system. So that means that our mole fraction of benzene times the vapor pressure of benzene plus the mole fraction of toluene times the partial pressure of toluene must equal the pressure on the system, and in this case that is 1 bar. Now again, this little equation here is the same as the partial pressure, so we can rewrite that as the partial pressure of benzene plus the partial pressure of toluene is equal to P at the bubble pressure. So then we can say the bubble pressure is equal to 1 over the summation of the partial pressures. Or we can say, from the original equation, the mole fraction of the vapor times the total pressure. From this, we can deduct the bubble temperature. By doing that, we have to use the Antoine equation, which is log base 10 times vapor pressure is equal to A minus B over C plus T. We can find A, B, and C. Those are just constants for each different chemical or chemical formula, benzene and toluene. So we can find those. So to find the temperature, the bubble temperature for benzene, we would need to do log base 10 of the vapor pressure of benzene, A1, B1, C1 plus T. We can solve for temperature for that, and then the same for toluene. And that is how we find the bubble temperature. It is also good to note that the bubble pressure and bubble temperature are inverse functions of each other, so when we code that out, you will see that. Now, how do we find the composition of a bubble? We can do that simply just by taking the mole fractions of both of these. So, composition of the bubble for benzene is going to be partial pressure of benzene over the partial pressure of benzene plus the total pressure, and then the same thing for toluene. Just like that. That is how we find the composition of the bubble. Alright, now we need to look at the dew point. The dew point is the point where the first water droplet forms in a system filled with vapor. So if we look at our pressure versus temperature graph here, say we are in the complete vapor range here, the dew point would be the point along this curve where the vapor at a certain temperature, at a certain pressure, becomes liquid again. So I think for water that's 1.01325. I'm not 100% sure, but that would be the dew temperature, dew pressure for water, and that is the dew point. So say we have a system of vapor that is 0.3% benzene and 0.7 mole fraction. That's how much the mole ratio of toluene in there. The mole ratio of benzene 0.3. Say we know the temperature, so we need to find the pressure. What's the pressure? Well, the first very important thing to note here, make this even, is that the mole fraction for water, the sum of these for all of the different parts, must be equal to 1. Now that seems obvious, but it does get a little bit confusing. So with that being said, we have our equation here. And we need to solve for the pressure of the dew point. We know that that is 1. So when we go to solve this, and we get this by itself, we get P1 all over Y1 times P, right? No, that goes on bottom. What am I thinking? Equals we get over that. So then we can sub in the benzene and toluene. We get 1 is equal to 0.3 times the pressure all over vapor pressure of benzene plus 0.7, which is toluene, times the pressure over P2 saturated. We can then pull out the pressure. So we have 1 is equal to 0.3 times that plus 0.7. And then we can isolate the pressure solve for it rather, and we get the dew pressure is equal to 1 over 0.3 P1 sat plus 0.7 P2 sat. Vapor pressure, saturated pressure. I want this to be longer. There we go. So then we can deduct that the dew pressure is equal to 1 over, and that just reminded me of an error I made, or made me realize an error I made. 1 over the summation of the vapor fractions time over the vapor pressure. And that made me realize that this is not 1 over. I don't know why I did 1 over this. It's just supposed to be that. And that's not supposed to be y, is it? Am I losing my mind here? No, this is just I'm losing my mind. I don't know what I was doing. This is just the summation. The bubble pressure is just the summation of the mole fraction times the vapor pressure. I don't know what I was thinking. Glad I caught that. So that is our dew pressure, 1 over the summation of the vapor mole fraction over the vapor pressure there of each individual component. Let's make that a little bit bigger. So then what about the dew temperature? Well, remember how I said these two, the bubble pressure and the dew pressure, the bubble point and the dew point are inverse fractions of the different components. The dew pressure minus the pressure on the system, if the equals 0 when the temperature of the system is at the dew temperature. So when we go to code that, we just need to do a function in a root solver to figure out, set the temperature to be 0, not the temperature, this to be 0 when the temperature is what it should be. So that is how we find the dew temperature. So let's go code.